Assalamualaikum warahmatullahi wabarakatuh. My name is Rafiq Akmal bin Muhammad Zakaria. I'm from BNM, Mechanical Engineering Technology Manufacturing. So today I would like to present my PSM2 project, which entitled Simulation and Experimental Wear Test on Amphibious Excavator Track Chain Components. My supervisor is Technologist Dr. Muhammad Farid bin Shahari, and my co-supervisor is Associate Professor Dr. Chan Chi Ming. Obviously, I'm from FTK Mechanical in the Faculty of Engineering Technology. So this is my poster, right, for this project. This is the abstract for this project. You can read here. So for the introduction, this research is mainly to test the track change of amphibious, the variability and durability of the track chain components of amphibious excavator. So what is an amphibious excavator? Amphibious excavator is an advanced excavator which can perform its tasks on muddy soil, swamp and shallow water, different from the normal excavator. The lower part, you can see on the figure is the lower part in the circle here is called undercarriage. This undercarriage consists of track change and other parts. So this research is mainly to analyze the variability and the durability of the track change components. As since this amphibious excavator is widely used in extreme condition of the construction site. So the objectives of this project is to assess the wear area of the chain components using numerical simulation software, which is SolidWorks. And the second one is to demonstrate the mechanism of the test fixed operation with the aid of animation, also using SolidWorks. And the project scope of this research is to assessing the wear area of the chain components using FEA analysis or we know as finite element analysis through SolidWorks simulation, specifically using static analysis, static study. The next is develop an animation showing the mechanism of the test rig using SolidWorks motion study feature. So the methodology or the method of this research is, first one, we start by planning the project. We do some literature review about the facts and info for this project. So the components we have given to us is then we reverse engineering or redraw using SolidWorks. So the components is the components of the track change itself. So the drawing of the components, we assemble them together to form the actual system, or we can illustrate the actual system. So this research is diverged into two main objectives, as I mentioned earlier. The first one is we do the simulation study, finite element analysis, and the second one is animation. So the animation is just basically we do a motion study on the components. The animation gives the general overview of the actual test rig for the research. And the next one is finite element analysis. After we assemble the components, the assembly, we create new study, which is a static analysis. We set materials, which is cast carbon steel. Then we set some boundary conditions. We set some fixtures. We set loads and forces and whatnot. Then before we run the simulation, we create mesh, the meshing, then we run the simulation. So if the simulation failed, we jump back to set the boundary condition, and then we do all over again to get a successful result. If the the simulation is success, then we analyze and we discuss the results and make the conclusion. Alright, so this is again the method for the finite element analysis. First, we assemble, of course, we assemble with components. We create new study, set the type of study, which is static analysis. We set the material, which is the cast cover steel. We set the type of connections and whatnot. So next one is set the fixtures, fix the geometry, the rollers and whatnot. So the next one is external forces, which the force applied through the components of the system. Then we mesh and run. We see the result and then we analyze. So this is the results. The figure here is the figure is shown the mesh quality. This is before the simulation. Before we run the simulation, the machine is required for the numerical calculation of the SolidWorks itself. It is an integral part of the engineering simulation process, where complex geometries are divided into simple elements that can be used as discrete local approximations of the larger domain. We use a blended curvature-based mesh to get more precise and more accurate simulation and calculation. The figure next is the figure shown here is the results of the simulation. The figure shown here is a stress contour plot. The stress contour plot is the result of the simulation and calculation done by the software. The colored contour is shown on both link extended and holding rod. The stress is not shown. The colored contour is not shown on the roller and in the slot because these two components is set as fixed geometry. Right. As we can see the pattern here, the maximum stress is 7.184 to the power of 6 Newton per meter squared, which is indicates by the yellow region. And we can know that the yield strength of cast cover steel is 2.482 to the power of 8 Newton per meter squared. So we can say that the maximum stress does not exceed the yield strength of the component. So this figure here shown the cross-up view of the link extended. So the stress is focused more on the region near the holes here, as you can see. This stress might cause the holes to loosen or breaks. This loosen the holding rod that comes through the holes from its position, and this eventually the hole will make the whole chain will integrate. Right. So this one is the close-up view of the holding rod itself. The maximum stress also experienced on the holding rod, and the stress much more focused on the middle part and center of holding rod. Since the maximum stress is not exceeding or below the yield strength, this failure does not occur. However, in the long run, the rod might wear, resulting in a necking-like shape. Alright. So we can see that the stress experienced on the upper and the lower part, but we know that the chain is moving back and forth, right? So and this holding rod is actually rotating on its position. So this might we can say that in the long run the stress resulting making like shape at 360 degree. So this is the simulation or the animation, sorry, of the to give the general overview of the actual test rig. Right. So this is the the front view of the animation. And this one is the upper view of the animation. Right. So the conclusion is the simulation has been done successfully. The stress is identified on the holding rod and the link extended. The maximum stress is 7.184 to the power of 6 Newton per meter squared. The yield strength is 2.482 to the power of 8 Newton per meter squared, which is the yield strength of cast carbon steel. That means our maximum stress is not exceeding or below the yield strength, and that this we can say that failure does not occur, but in the long run the region experiencing stress will eventually wear. And then the animation does show the general overview of the actual test rate. The general overview of the test rate. Alright. Okay, so this is my references for this project. And thank you. Alright, that's all. Thank you very much.